Okay, now I think uh, this is the last discussion, right? And I think I need to complete this. Okay, so let me just review for this example here. So, and this is a particular usual questions that might come in calculus, especially for parametric equations. So first is finding the tangent, okay, finding the tangent within certain points, and then you need to know whether the tangent is horizontal or vertical, and you need to find where those points are. And the third question that haven't been answered yet is to find the concavity, or where does the curve is concave upward or downward. So let me just put this a little bit over there. And just a reminder, to find the concavity, what you need to do is to find the second derivative. So this will be, let me write here, this goes to be the second derivative, where you need to find this, okay? Or you could say y double prime, where this is have this two statement. When you have positive second derivative, this will be concave upward, this will be concave downward, okay? And then we can try to work on the second derivative for this one, for the parametric. Remember, we try to find the second derivative through this statement here. Okay, so we are going to write the dy dx inside here. So let's just write first 3t squared minus 3. And then what is dx dt is 2t. So we just write 2t. Okay, and then we can start to, so we need to derive 3t squared minus 3 over 2t. Oh, what's that? Okay. And then this will be a quotient rule for derivatives. So let me write here. This will be 4t squared. 3t squared 60, right, 60 multiplied by 2t minus 2 3t squared minus 3, and get a long. Okay, I think that's settles things. So let me just complete this. This is 12t squared minus 6t squared plus 6. Right, or we can write here 6t squared plus 6, right? So then this will be 6t squared plus 6 over 4t squared, but I would like to multiply with the half t, or let me just write this is over 2t, and then I will cancel this out. So then it will be 3t squared plus 3, and this will be 4t cubed. Or I think I just multiply this to make or to avoid confusion. This will be 8-3 cubed, right? So this will be our second derivative. So you see the way we see our first derivative and second derivative, because it's already in form of dy dx and this squared y dx squared. This will be very the same as what we did in calculus 1. So it's directly this dy dx is the slope, the gradient, and this one will be we say if this is equal 0, and we can find that it is true that we can find some equation that is equal 0, then that will be our inflection point. If you remember, we have the slope and we have the inflection point, okay, or the extreme point in the first derivative. So we're going to find where this going to be positive or negative through this equation here which we got. So from here, what can we do now is basically the one that we could take some trial is probably take t equals 0. So let's say we have t equals 0 here. Because 0, if we imagine in this equation, 0 could make this undefined. So this is something that we don't want to be in our equation. So if we take this t equals 0 and we see when t is positive, all will be positive. And since it has cubic, when it's negative, it will be a negative. So when we take, for example, minus 1. Minus 1 in squared is positive, so we could ignore that. The one that is make difference is this cube, right? So if we take negative here, it will be change all the negative. If it's positive, it will be positive. So we get directly the difference in this concavity, right? When it's less than 0, it will be downwards. When it's positive, it will be upward. Okay, so we get that here. This will be concave, or let me write with the right color. This will be concave downward. This will be concave upward. Or this is t less 0. This is t greater 1. 0. Sorry. So suppose that we have all the information we need, okay? So we have the equations for the tangent at 3, 0. We have the vertical tangent, we have the horizontal tangent. Including all the parameter t, okay? So we could try to make this graph, okay? So the fourth question is sketch the curve. Okay, so how do we sketch the curve? We can sketch the curve taking some points, here, or we could perhaps start from this 3, 0. Okay, we could make this by taking some t, okay? And then we know that from the vertical tangent and horizontal tangent, we know which t that we supposed to do. Okay, so we could have from here, and if you check through our concavity, when t is less than 0, it's concave downward. Concave downward is something like this, right? And where is t equal -1? Okay, let's say it's -1. Here's -1, and then we see that it is concave downward, right? And when we have the t equal 1, or when this is a positive, this is concave upward. So it's actually similar to what we have in calculus 1, but the difference is it is in the parametric curve. Okay? So now the idea of the dy dx and the second derivative is we need to match with the parameter t. Okay? in calculus 1, we only deal with the y and x, or we could just find which x that is going to be inflection point, the local maximum, local minimum, etc. But now we are going to change not only x, but we need to find in which parameter t. That's the whole idea. Okay. 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 Okay, I think later on, maybe if you have time, we can review for more examples. Okay. So in this example, it's all related to graphing calculus. Okay. In calculus 1, including finding the tangent, and then checking using the second derivative test, and then first derivative test to find the first derivative, second derivative, and then find the extreme points and the concavity. Okay, now let's continue to the second part on the, so first is tangent in parametric. The second part is the area. Okay, here's the area here. So we know that the area under the curve, let me put this aside first. Let's say we have a function and then define from a point to another point, and we know this is the area is going to be a b integrations f of x dx, where we need to define that this should be a positive functions, at least it's 0, and then let the curve trace out once. Okay, it means trace out once means there is no loop. Okay, we need to assume that first by another functions which we include the parameter, let's say f of t and y. And then we need to also define our parameter, which is we need to have another symbols, let's say alpha and beta. Now we can calculate the area for the f of x. Since f of x is y, okay, so we could substitute like this. Let me make it bigger. So we could substitute y with g of t, okay, and dx we could take from here and then write the f prime t dt. So let me write here to help you out. What does that mean? So we have x. So if we derive this, with respect to t, we have this. Okay. So f of x is y, okay, so this y here, and y is also g of t, and then dx is we are going to replace with this f of d, and we derive so gt f prime t dt. Okay, I think it's quite intuitive using the chain rule, and then based on the definition from the x, y, and then parameter t. Okay. Okay, we have this, or we can also switch the alpha beta, but this will be the default on the area in parametric. Another way to intuitively understand how we does it is basically just substitute everything. So alternately, let me make clear trace.
Thank you.
Is that clear? If you see any word that is not clear, let me know. Okay. So alternatively, let's say we have y dx, okay, and then this is a b, and suppose that we have changed everything into parameter. So what we can do is actually, so let's say this is becoming the alpha and beta. And then let's say y is also, we could, like, if we are just using y without the definition from above, okay, and then you don't want to memorize all of this, let's say y is also y of t, okay, you could also it means that you could write the function of t of y, I mean the same thing as the above. And then for dx, we could write this, and then it's perfectly fit with our chain rule. It's the same thing. The same thing with this one. And remember, for this area in parametric to be works, we need to have this trace out once, okay? Only one. Okay. It means there is no loop, for example. Okay, stop. If we have like that, it doesn't work. In this case, it doesn't work for area. Because if we have traced out more than once, you will have difficulty on defining your area itself. Because you want to have, like, you want to, for example, let's say something like that. Okay, you want to know this area. But what is the area under the curve? Is it this or the whole thing? Because if you force out yourself to work on this with, like, for example, you have the functions and then you try to work on this and calculate, your answer will be not the same as this area. Okay. So if something happened like this, there's some tips for you. You could split the image. For example, if this is a circle, Then you could just make it just one area, and then you have the half part of it, and then you just multiply by 2 to make the area. Okay. The same thing happened later with the arc length. Arc length also need to trace once. Okay. You need to trace once, because if not, then you will have double. Okay. So that means if you have this kind of loop, what you can do is maybe you can cut in half, and then to make sure that you complete the loop, then you can multiply by 2. Okay. Sometimes it works like that, but it also depends how symmetry is the functions are. Okay. So you need to also be careful on that. Okay. So symmetry, I think, will be important. Okay. Let me write here just to make sure. Be careful on loop. Okay, now let me zoom out this and see on the right side. Example 3, find the area under one arc of the cycloid. Well, what is cycloid? I will just explain just a little bit here. So cycloid, let me explain from the beginning, okay? Just to get you understand what is happening here. Okay. So suppose that we have a circle here, or maybe you could imagine the circle like your bicycle, and then you have your point P, which touching the ground. Okay. Imagine this tire or the circle is rotating and it's moving forward. At certain period of time, you will see the point P will change its locations, right? Okay. So maybe sometime here, maybe if we go here, maybe P is going, maybe going here. And then if you move again and again, your P will also like moving, right? And how the P changes, it will create a trajectory. That's what we call the cycloid. Okay, so the cycloid is something like that, and then like that. Okay, and then move on like that. That's how the definition is on the cycloid. Okay, and there is some equations that derive from this cycloid, but I will just give you what it is from this equation. X equal r multiplied with theta minus sine theta, and y is r multiplied with 1 minus cosine theta. If you are interested to learn more, I think maybe later on I will provide, not in class, maybe just additional video how to get this formula. But our idea is now we are going to try to find the area under one arc, which means if this is a cycloid, then we just need one arc, okay? And then we compute the area, okay? So one arc, to be precise, let me just draw again. Let's start from the beginning of the origin. Let's say this is 0, and then let's just focus on this part, okay? So let's say this is one arc, okay? One arc of the cycloid. And how much the distance? The distance, so the P goes back to where it belongs, to downside, which means it's the, what is it? The circumference of the circle, which is, this is equal to 2 pi r, okay? So we are going to take this area by taking integrations from 0 to 2 pi r. Let's just write y dx first, y dx. And then our parameter based on the equation here is the theta. So let me write here, x is r theta minus sine theta, and y is r1 minus cosine theta. Okay, let's change everything into parametric. So this will be integration. And now we change also the endpoints to parameter, which results in 0 to 2 pi, okay? And y is r 1 minus cosine theta. And then let me write here the dx dt or dx d theta is r 1 minus cosine theta, right? R is just a constant here. So this will be r, and this is practically the same thing. And then the theta. We can factor out the r because that is just a constant, so r squared outside. And then this will be 1 minus cosine theta squared, okay? And then what will happen now is we are going to expand this. So this will be 1 minus 2 cosine theta plus cosine squared theta dt. Okay. Now remember, this is, I believe, will be something that might appear a lot. So if you have trigonometric quadratic like sine squared or cosine squared, remember the best way to deal with that is change to double angle. Okay, change to double angle. If you forget double angle, you can remember this part. Okay, so this is the basic. Okay, so you could get this, or okay, now change this part. So r squared, we still write this. Now cosine squared will be plus half plus cosine 2 theta over 2. Okay, changing from the double angle formula. Okay. So let me write here 3 over 2. Now we integrate this. Negative 2 sine, and then cosine will be plus sine 2 theta. So over, supposed to be over 2, so over 4, right? So over 2 multiplied 2 is 4, right? And then taking 0 to 2 pi, I think sine all 0, right? 2 pi and 0, it make it 0, so we could just multiply with the 3 over 2. So this will be r squared multiply 3 over 2 pi, which is 3 pi r squared. Okay. Maybe before we continue, is there any questions first? Is there any questions? I think example and formula are not that difficult. The difficult part is the maybe question from the textbook. Okay. And sometimes the most of my exams, I think I'm taking it from textbook. A few of them I'm looking from other sources. Okay, so my plan today is getting this area, and then after this the arc length. If we have time, we can have some review, some exercise on area and arc length, or probably the tangent from the previous one. And then maybe opening new introduction to the next part of parametric, which is the polar. So chapter 10 has two subtopics. So parametric equation and polar curve. Okay, I think I can go to the next one. Okay. So now is the arc length. Arc length, as you know, and we already described in more details. So basically, we are trying to measure the length of the curve. Okay, that's the arc length. So I'm just trying to describe this based on the textbook. So basically, the arc length in parametric, okay, in a parametric system, the difference is now we are going to apply the mean value theorem to our parameter interval, okay, which we call the t. Let me start to write what we know before. Okay, so we know that the arc length, generally it has this general formula, dy dx squared dx. Okay, and then if x is f of t, y is j of t, and then we define the t in between alpha and beta. Also, we define that dx dt need to be a positive. Well, what does that mean? We need to define this as a positive. It means that the curve C, we need to trace or traverse once from left to right. Okay. So similar to the area, the arc length also we need to assume that it is going to move or to traverse, to trace once. Okay. And so basically, from this formula here, if you see this part here, let me zoom out a little bit. We substitute, let me write here, that is going to substitute. So substitute the dy dx with the parametric dy dx, okay? And then take the squared. And then substitute dx with dx dt multiply dt, okay? Take this substitute and then use the chain rule formula. And then we simplified, okay? We simplified, and then we get the L is this, okay? And remember that dx dt should be a positive, okay? So we ignore the negative one, okay? So that's why we can simplify into this that L formula. The left notes is just to describe in a more official way to describe the parametric arc length. Okay, it is very similar to what we have in the previous arc length. The difference is we describe this through the parametric t. Okay, so the mean value theorem, instead of the x, we get into the t. So we change everything using substitution and chain rule to t. And same thing happens with this, with the delta. And the delta we substitute back to our system in this limit. And then by definition of limit, this limit is equal to our integration. Okay. This, which means going to equal to this. Okay. So you could have two different perspectives. Intuitively, you could do this directly using substitution and chain rule directly, or if you want to approximate through limits, you could do this and then change everything from the scratch. It means that from the official definition, the distance between these 2 points, take the limit, and then this distance can be applied using Pythagorean, and then take the mean value theorem for this to substitute back, and then getting this. Okay, so the square root, remember, every time you have the arc length, why arc length have the square root? It's from the Pythagorean theorem. Okay? It's from Pythagorean theorem. So the square is from Pythagorean theorem, which you can apply from any point, and then you could just make a triangle, and you could get the Pythagorean from that perspective. Okay. And then from here, you take definition of the limit and integration. You get the same formula. This is from more definition through limit, and this is from the intuitions using chain rule and substitution. Okay, so both are getting the same conclusion. Okay, the same conclusions. There are some process that I'm skipping. If you want, you can remembering through this this P is actually, we could write as this. And then it goes to be here. And then change the delta with the substitutions, delta x and delta y, we substitute with the one we provide from the mean value theorem, and then we get the final conclusions. Which the final conclusions is pretty similar to this, or we could write the L as alpha beta, and we can write this is in terms of f prime and g prime. And this is dt, okay? The same thing. Okay, maybe let me just write, or giving you this, practically the final theorem for the arc length. I think you could, if you may be confused on what happened here, you can focus here, which we have the conclusions and all the assumptions that I have previously mentioned, which describe the parametric equations, and then they need to be, the first derivative need to be continuous on the interval, and then the curve itself is traverse exactly once. So again, no loop within this assumption. Okay. Yes?
What's a double star? Delta Y P.
This one?
Yeah, double star T. What's that? Is it mistake?
I think that means the sample points. Okay, the same thing with the first asterisk. I think not really having differences. Okay.
So it's just the same like a T with one star.
I think that is going to be distinguished between the first one here and then the second one that is going to be here. Just to make it different. This is for the x and this is for y.
Ah.
Because if this is the same, maybe you will find some confusion. Okay, just to make sure that it's separable. Okay, I forgot to add the surface area, but let me add after this part. Any questions? No? So from this arc length, we could devise the surface area formula. Basically the same thing. It can be 2 pi x ds or 2 pi y ds, and ds is basically this arc length, okay, this parametric arc length. Okay, let me continue a little bit, okay, before we take a break. So before we are going to have more exercise, let me add the surface area very quickly, because it has the same formulation with the arc length. So let me add, I forgot to add here. So basically, suppose curve C is defined by the parametric equations like this. And we have the alpha to beta for our parameter. And then we define that the f prime and g prime, they are continuous. And then g of t is a positive function. And c is traverse once, okay, as t increases from alpha to beta. I think my words is not clear. As t. Okay. Okay. Now if C is rotated about x axis, then the area of surface, or here is the surface area, is this. Let me just write this first. Okay, that's the idea. Okay, so basically the same formulations, but you change all the parametric. Okay. Okay, we will have a break and we can continue later on. Okay, so the surface area basically the same thing. The difference is we are going to change all the formulations into parametric. For example, if we have y, like it's a function of t, then we change all it into t. Okay, and then we use the ds that is from the arc length, the parametric arc length. Okay, and then how we see the surface is basically depends on how the conditions. Okay, for example, it can be 2 pi y ds or 2 pi x ds. Like if you have the shape like this, for example, if you have this shape and then you want to rotate through the y-axis, of course, the logical reasons is going to take this as your radius, right? So this is your radius. So x is your radius. But now, y and x, they are both in function of t. Okay, so we are going to change all into this t. So it can be f of t or g of t. Okay. So you can have this or this. Okay. And I think the way we use it is basically the same. Okay. So I think we are now reviewing some exercise, some practice, maybe 2 or 3 questions, maybe just 2 at most, and then we go forward to the polar. Okay. Okay, maybe 30. Maybe 34. Okay, 34 or 33 is, I think, too simple. Maybe 34. 34 and which part do you want to take? The area or the arc length? Huh? Area? Which one? 37 or 38? I provide two. How about 38? It's interesting, the shape, right? Okay, let's check. Let's check these two. So 34 and 38. So I hope you can check. And later, maybe you could check also at home. Every week I will upload the notes. So I will upload maybe next class, okay, after next class. So check the notes that I'm prepared through Moodle. So basically, number 34 is pretty similar to the example we've done earlier. Okay. So we need to find the equation of the tangents, which means if you look at the question, it's asking you to find the tangent. So the idea is to find the slope. Okay, that's the slope, or it's dy dx. Okay. We have the x in parametric, y also in parametric. So we know how to find dy dx through that parametric. Okay, so we get the slope, and then we get the point 43. 43 is xy, right? 43 is xy. We need to find at which t does it fit with the system. There will be a little bit algebra inside, some quadratic equation, I think. So I hope you can try to solve. You could try the algebra itself. Okay. So 34, we could start to find, finding the slope. We could write finding the slope means that let's write x is 3t squared plus 1. So dx dt is 60 and y is 2t cubed plus 1. So dy dt is 60 squared, right? And usually the most frequent mistake is to write dy dx. Sometimes you switch the dx and dy, okay? So don't forget that it should be dy dt first and then divide by dx over dt. Sometimes, in my experience, because you are doing the dx dt first, when you write the dy dx, you write the dx dt and then dy dt. Okay, so this is the common mistake that I've seen so far. So this will be done by 60 squared. 60 is equal to t. So if you want to write like the line equations based on this x and y, for example, this x and this y, and using this m, remember that this is m, okay? We could write linear equation y minus y1 equal m x minus x1. Like in terms of, we're still in the parametric variable. Let's say we are going to write this y minus 2t cubed plus 1. This is t x minus 3t squared plus 1. Okay. The line is passing through for 3. Okay. It means this line, let me resize this to make it more clear and more space here. Okay, line is passing through this point, so which means that we can substitute x and y. So we can write here and perhaps we can solve it. So negative 3t cubed, it will be plus 3t cubed minus 2 . So t cubed here, and then 40 negative 1 3 4 minus 1 is 3. Sorry, this should be 4t minus 1t is 3t, so plus or minus 3t, and then 3 minus 1 is 2, so plus 2. Okay, now we have the cubic t cubed minus 3t plus 2. How to factorize this? So it's not a quadratic. I expect this to be quadratic, but it's cubic. So what should we do now? So let me give you some tips. Okay, if you have like a polynomial conditions, you could do polynomial divisions using syntactic divisions, especially, and I will say that our factors will be plus minus 1 plus minus 2. So we could check 1, negative 1, negative 2, plus 2. Okay. How do I get this? This from this one and this one. Okay. But I don't have time to explain, so I will give you the general idea how we should do it. So we could write 1, 0, negative 3, 2. I think you have done this, I think. Some of you have done it in high school. Some of you done it with me in Basic of Math, if you have taken the course, if you remember the course. So maybe taking 1, okay, maybe this will be correct. So 1, 1, 1, 1, negative 2, negative 2, 0. Oh, this is our factors. So we get 1 is our factors. So we could write the equations become t minus 1, and then write down t squared minus t, plus t, let me write plus t minus 2 equals 0. I think we can factor this, right? This going to be, right? Negative 2 plus 2, okay. So we get this factors. So t equal 1 or t equal negative 2. So bring back to what we have at the beginning here. Let me copy again this part. And we can substitute t equal 1 or t equal -2. So let me change the color. Let me write with green. So when t equal 1, that will be y minus 3 and x minus 4, right? Or y is x. -4 plus 3 is -1. So this is the first tangent. So there will be two tangents at this point. Okay, let me move this to the left, and then I will write another one when t is -2. -2 cubed is -8. -16 plus 1 is -15. So y plus 15 equal, I think I need to write this, -2x minus 12 plus 1 is 13. So this will be -2x plus 26. So this will be y equal -2x. 26 minus 15 is what? 11. 11. Okay, that one. Okay, I expect to be short, but I think no, it's not short. Okay, that's everything. So the equation of the tangent, we have two. Okay, we have two tangents at that point. Okay. Okay, so every time you get a polynomial, this is, I think, really helpful if you remember the syntactic efficiency. Especially you have cube or maybe with the power of 4. And then you could try trial and error. For example, here is t cubed. Only one coefficient is 1. And the last part, the constant is 2. Okay. So we only see the last and the first, okay, for the syntactic rule. 2 divided by 1. Okay, that is how we see. So we are going to see the factors, the common factors from 2, which is having 1 and 2. So you could try -1 plus 1, -2 plus 2. And that's the 4 numbers that we could try. But you could always try from the easy one, either 1 or -1. If you get that is 0, then that will be your factors or your zeros. And then you can just write the rest using the expression from the last calculation here. Okay. Okay, let me copy this page first. Let me duplicate this. same thing, and then I will erase the right part.
What does it mean our function contain have two has two tangents in one point?
Maybe you will have loop, maybe something like that.
And somewhere in this over here.
Yeah. This one here. We have this, and we have this. Because in parametric, we can have like something like this. That's why we have two equation of tangents. Okay, if the equation is simple enough, if you see our equations from the question, we have 3t squared plus 1 and then 2t cubed plus 1. If you want to try substitute, because it has square and cubic, it's not really that easy to get into. So the idea is we need to find the t, right? We need to find t equals some numbers. But if we try to substitute the x and y using the 4, 3, and we just make 4 into here, and then we get p equals something, something, and 3 here. And if you want to make sure that this is correct, maybe not so ideal. It's a little bit different from what we have in the example, which we can substitute and see, and we can try the p, and then it's exactly the same. But since it's not ideal, then we need to just go through and just use it as it is. So using y in these terms here, and using the x in these terms. And then with moving forward, taking the point, put inside the y and x, 3 and 4, and then we could get the whole formula for t. And from here you can get t. That is from this polynomial equations. Then you get t, which you have two t's, and then from these two t's, we could get two different equation of tangent. Okay. Is it difficult? Difficult? So? Could be worse. Okay, that's helpful. Okay, so okay. I'm not sure, but let's try the area first. Okay, let's try the area first. Okay, now let's move on to the second questions, which is the number 38. So since this is the same, so I will erase this part. So let me just erase this. Okay. Don't worry, I have the original one on the previous page. So let's try number 38. Let me zoom in so that you can clearly see the equations. So we have x equal t squared minus 2t and y equals square root of t. The question itself is find the area enclosed by the parametric curve and y-axis. So you have the picture. So what should we do is we are going to define that this is our area, right? So what should we try to do now? So first, maybe let me just write down the parametric. So x is t squared minus 2t, okay? And y is square root of t. And they both intersects y-axis when x is 0, right? Right. See this, okay, and then that. This is when x is 0. Okay, agree? So when x is 0, we could know from the expression of the parametric x, which is now it's 0 like that. We could solve this and find that we could have two different t, right? We could have t equals 0 or t equal 2. And since we are going to evaluate, I think, these 2 points, so we are going to evaluate based on the endpoints on 1, right? We have t equals 0 and t equals 2. Then we need this to put inside our y, because we need this y for our area here, right? Okay, so y is square root of t. It means that when t equals 0, y is 0. When t is equal to, y is square root of 2. Okay? So the shaded area, then, the area will be from 0 to 2. I will write, as in the calculus 1, the right xl means the curve on the left, okay? Curve on the right minus curve on the left, dy. What is the curve on the right? This x equals 0, okay? The curve on the left is this x, okay? And then we are going to express this using the parametric expression. So we are going to exchange all this into parametric. Okay? Oh, sorry, this should be square root of 2. And now we change to parametric, okay? We change to parametric, so t equals 2, or t equals 0, t equals 2, okay? So let me write 0 so that you know that this will be the x equals 0. And then minus, let's just write in terms of parametrics x of t, which we have here. Okay, later we can substitute. And then dy becomes dy dt. Okay, so dy dt, or you can write y prime t dt. Okay. So in the integrations, you could start with the original integrations, okay, before you change to the parametric. Okay. This could help you to illustrate with the picture itself. So you could still use the techniques in calculus 1 for illustrations. Okay. So this will be perfectly, we could take this dy, okay, and this will be the curve on the left, this is curve on the right. Okay. I hope you still remember calculus 1. Okay. For example, if the curve is something like having another one like that, then this will be the curve minus this one. Okay. So I think we can exchange all, and then we take the derivative. So let me write here just to take the, so y is square root of t, dy dt is 1 over 2 square root of t, right? So this will be 0, 2, and then let me put the negative on the front. Sorry, put the negative here. And then x is t squared minus 2t. dy dt is 1 over 2 square root of t dt. I think that we could do that, and we could basically compute these integrations. It's just a normal integration with with powers, right? So I think I will move the half inside. 2 minus half. So 3 over 2, right? 3 over 2. Minus 2 is cancelling. 1 minus half is half. So t half. Okay. I think we can integrate this, right? So we can integrate, put negative in the front. So plus 1 is 5 over 2. So t 5 over 2. 2 over 5, so it will be 1 over 5. Minus 2 over 3, t 3 over 2. Okay. If you have a problem within the calculation, let me know. This is just a normal integration. And then put everything inside, but I'm too lazy to work on this. You can use calculator if you want. 2 with power of 5 is 32. 32, take the square root of 32 is 16 by 2, so 4 square root of 2 let's just write 2, so minus 1 over 5, 2, 5 over 2, minus 2 over 3, 2, 3 over 2. And 0 is just 0, so this will be that. This is 2 square root of 2. This is 4 square root of 2, right? So I could take out square root of 2. Or just 2 square root of 2. And this will be 4 over 5. Minus 4 over 3. Okay. Okay, I think I will just stop here. Maybe one more question from the arc length here. But I think you could skip the 49. So 47, 48, or 50. Any question first for this part, the area? Maybe you have confusion. How does that happen? Well, this first part here is from the calculus 1. If you have something like this, it's better if you just see from this perspective, right? If you see from here, you know the area under the curve or the area between curve is the curve on top minus the curve on the bottom. And then it is the same curve, right? So it doesn't work like that. So we need to change the perspective and using the dy and see that, oh, we can have this as a left curve and this is a right curve. Or we could see this, or maybe this is better. Okay? It's more consistent. So this, the top minus the bottom. Hmm? Which one? This one?
I mean, source integral.
XR is function of y. X equal function of y. The right one minus the left one. Usually, if you remember the area between curves, we have something like this. So you have this, here this is the y equal x squared. And you have this, y equal x. Find the area here is x minus x squared. It is actually y at the top minus y on the bottom. This is yt and this is yb. And this is case of y, so function of x. But in that case, if we have, let's say we have this parabola, okay? Let's say this is x equal y squared. And then maybe, let's say this is the y equal x, or x equal y. How to write the integrations? This will be the top and this will be the bottom, or right minus the left. Okay, this is the area here. So this will be XR minus XL, which is this y minus y squared. The same thing. Okay. Yeah. Okay. The same thing. So we treat the XR as this x equals 0. Okay. This x equals 0. Our equation minus this one. Okay, maybe one more. How about 48? Because 50 is too much algebra and trigonometry. I hope you can do that for exercises. Maybe 48. Okay. 48. I will make this as a duplicate. So, okay. So I will erase this. Okay, if you want to take a picture or you want to take notes, you can take picture first. Okay, I will erase this part and do the number 48. Okay, so 48 is, let me write here. We have x and we have y is 4e t over 2, and we have the distance is from 0 to 2. And because there is nothing more in the information, then we could just directly go throughout the formulation of the arc length, which is, first we need to find the x dt, which is the first derivative with respect to t. So e with power of t and then minus 1, and then dy dt is basically half 4 is 2 e t over 2, right? And then we could take this, take the squared, take the squared, take the squared, or let me just write here to make it easier. Okay. And then we could plus this 2. So dx over dt squared plus dy over dt squared. Let's open up the quadratic and make an expansion. So e to t minus 2 et plus 1, and then plus 4 et, and then solve this, simplified, plus 2 et plus 1. Now notice that it is exactly the pattern that I suspect. Our first expansion from here is this one. After we compute this, we get this, which is precisely the same, but the difference is this. So notice that we could bring back this into this perfect standard form, right? Okay. So this is, we could write e t plus 1 squared. Okay. So our arc length 0 to 2 of this okay, and then we could cancel the square root. So I will just write this and take the integrations. So So e is still e with power of t plus t from 0 to 2. This will be e squared plus 2 minus 1. And then this will be e squared plus 1. And then, yeah, 48 done. Okay, so as an intro, I would just want to say before we move on to next class, we are going to describe this, okay, polar coordinate and the polar curves, okay. So I hope if you have references or some tutorials how to do the polar system, you could find it, and I will try my best to also give you some resources for the polar system. So basically, the differences in polar is now we are not in the xy dimension or xy coordinates. We move away from xy to the r and theta system, which we call the polar. And how we move the polar is basically we rotate. So for example, if we start from the polar axis and we rotate from the polar axis, go here, anti-clockwise like that, or even move away, depends how many angle or how much angle we rotate. Okay? Maybe we rotate pi over 2, or even pi over 4, okay? Depends on that. And all the conversions throughout the system from the Cartesian to polar, we are going to use it all the time. For example, like r is r cosine theta, y is r sine theta, and y over x is our tangent theta. So we are going to use this for converting the xy Cartesian to polar. Okay, all the time we are going to see this. Okay? And we are going to elaborate more in next week. Not next week, next Thursday, this Thursday. And yeah, you have a, I think, break tomorrow, right? So hopefully that helped. Okay, I think this will be the end of our course now. So see you Thursday. Yeah. The previous one? Okay, this one? Okay.